Hi, this is Jack Jackson. Let's look at this time at another possibility that might lead to some triangles that are similar. This is the SSS triangle similarity theorem, or the similarity condition. Let's see what happens. I guess it remains to be seen if it's a theorem or not. We want to look at two triangles with the sides proportional. Now remember, to make two triangles similar, all of the corresponding sides must be proportional. So that would mean that say A, the length of this side here, BC, that's A, then the corresponding side here from B prime to C prime needs to be some constant times that A, and then the same constant times this length B from A to C is got to be the length from A prime to C prime, and the distance here from A to B is C, then K times C is this length here from A prime to B prime. Okay. In addition, all the corresponding angles have to be congruent. Now, so we're going to investigate if that works. So if you notice the way I constructed this, I started with just any old triangle here that's completely able to be manipulated and make it into any kind of triangle we want. And then what we did down here is we first made a line segment here that was the same length as this one. Now, the way I did this, I've got this where it's parallel to this one here, but that's not something it would have to be. This could be any length. I really didn't need to do that. Next, what I did is I made a circle here that was this centered at B that's the same radius as K times A. Right? So we know that C prime has to be on it somewhere. Then I also made a circle center here that was centered at A prime of radius K times B. Right at the moment, K is 2. And wherever those cross out here, that's going to be where we put C prime. And that'll make sure that this distance is KC, this is KB, and this is KA. Okay? I made those kind of light so they can kind of be out of our way there. And notice as I make K bigger or smaller, we have this. So if K is less than 1, it's smaller. K is bigger than 1. Okay, well, the question is then, do the angles turn out to have to be the same size? And if you look, yeah, they are. Corresponding ones are the same. Well, is that a fluke? Let's see. If we change this, we get different angles, but they're the same down here for corresponding pairs, right? Okay, and we move, say we move B around or C around, okay? We can get that. Over here, we can see the measures of everything, the measures of A, B, and C there, and the corresponding measures of the sides over here, which are K times that. We get the actual numbers in there, and then we get the numbers for the angles there. And so you see that it does work. So it looks like that SSS condition is enough to make the triangle similar. If you can get all the sides proportional, then for free, you get all of the angles congruent, and that makes the triangle similar. So this gives us a theorem that says, given two triangles, ABC, and triangle A prime, B prime, C prime, with some constant K equals A prime, B prime over AB, those are the distances from A prime to B prime is over the distance from A to B. And that's the same as the distance from A prime to C prime over the distance from A to C. And that's equal to the distance from A prime or B prime to C prime divided by the distance from B to C. If those are all proportional, all those fractions are equal to some constant K. In other words, all the distances down here on the second triangle are K times the corresponding distance on the original triangle, then it turns out that's enough to make the angles congruent, and we have the triangles similar. So let's look at a proof. Okay, and I've got this set up where you can slide through the proof one step at a time with the stepper here. All right, so if you've looked at my last video, you'll see a very similar setup, okay? In fact, if you've done that, I encourage you to stop the video right now. Think about how we proved the last one, and which was the side angle side triangle similarity theorem. Follow very similar steps and you can get a proof here. So I'd like you to actually try that on your own before you come back. So press pause now. So hopefully you're back and you tried this yourself. And here's basically how we're going to do this. So start by going out well, we state our given, right? We're given two triangles, triangle ABC and triangle A prime, B prime, C prime, with this setup here, sides proportional. Now, first of all, what happens if K equals 1? In fact, I can make it K equals 1 right here. Then, in fact, these two triangles are actually congruent to each other. So they are congruent to each other, but how do we show that? Well, we start with our given stuff here. If K is 1, they're congruent by the side-side-side congruence theorem, right? All the corresponding sides are equal length if they have that constant as 1. So we've proved that case, so we might as well knock it out. And now what happens? For now we can assume K is not 1. And in fact, we might as well assume that K is bigger than 1. And let's set it up that way for the rest of this construction to work. I need K to be bigger than 1. Well, what if K is not bigger than 1? What if K is bigger than 1, this one is, the second triangle is bigger than the first. If K is less than 1, then the second triangle is smaller than the first. Okay, well, what happens if the second one's smaller? No big deal. We just switch the letters, change the A's to A to A prime and A prime to A, and then proceed with the proof that way. So that's why we say without loss of generality, we can make that assumption. Okay, so anyway, let's keep going. The first step is we're going to go out on A prime to B prime a distance of C here. Okay, so go out here and make a new point, B double prime, so that this line segment is congruent to the one up here, that the distance from A prime to B double prime is the same as the distance from A to B. Okay, next we're going to use the parallel postulate to say that we can make a line segment congruent, or not congruent, parallel to this one over here, make a parallel line to this line B prime C prime, and then find out where it intersects this line is C double prime, and notice that that since this is the longer one here than that, we're going to get C double prime between A prime and C prime. Okay. Now we constructed it so these are parallel. Well, now we have a pair of parallel lines here and here, and this is, or if we extend those, we make parallel lines, and if we extend this guy out, we make a transversal to that, and we know that a pair of corresponding angles, those two right here, have to be congruent because of what I call the F property. If we have a pair of parallel lines cut by a transversal, corresponding angles must be congruent. Part of our transversal to parallel lines theorem. Okay. Now, this angle, of course, they share, so these two triangles, that is triangle A prime, B double prime, C double prime, and triangle A prime, B prime, C prime have two corresponding angles that, two pairs of corresponding angles that are congruent. Therefore, by the angle-angle triangle similarity theorem, we get that those two triangles must be similar. Well, what does that mean? Well, one of the things it means is that the sides are proportional. So it says if we take the distance from A prime to C prime and divide it by the distance from A prime to C double prime, that's going to be the same as all the corresponding, fractions the other ways. You can see it written out here. And that's going to be, well, we know that's, how do we know what that is? Well, we already know that this side, let's see, what do we know? We know that this side here, this is C and this is KC. So we know that this side is K times, so that is A prime B prime is K times A prime B double prime. So since these are proportional, all of these are K times as much. So if we divide this out, if we divide this length of this big side from A prime to C double prime by K, we're going to get this length here. And it turns out to be congruent to this one over here. It turns out to be B as well. And similarly, this side here is side as the length C, or I'm sorry, A, the same as that one. So, well, now what do you notice? That triangle and this triangle have sides all the same length. So, by the side triangle congruence theorem, those two triangles are congruent. Well, if they're congruent, they're similar with proportional constant 1. And so if this triangle is similar to this one here, this little one, and it's similar to the big one here, then congruence of triangles is an equivalence relation, so it's transitive relation. So the first triangle is similar to the big triangle. And again, with proportionality constant k. So we prove this side triangle similarity theorem. So now at this point, we have three different ways of showing that triangles are similar without showing everything in the definition. We have the basic one we did first, that was actually the hardest to prove, the angle-angle triangle similarity theorem. And then we had two similarly proved theorems, the side-angle-side triangle similarity theorem, and now we add to that the side-side-side triangle similarity theorem.